Hello, this is Thomas at Geon Technologies. In this video, we'll be concluding our series on Programmable and Persona Device projects by showing a demo of Ezra on an embedded platform, a Xilinx ZCU102 with an attached Analog Devices 9371 evaluation board using REDHAWK 223 that we cross-compiled using Yocto and our most recent meta-redhawk-sdr layer. We'll get into Ezra in one moment, so for now, let's take a look at what our node looks like. You're familiar with the GPP most likely, so the other two devices are the FPGA Manager and the ADRV9371 EBZ, which are the Programmable and FEI Persona devices in the system. As the name suggests, the FPGA Manager Programmable Device interacts with the Linux kernel's FPGA Manager interface to load hardware for any associated Persona device. For its status list, you can see the ZincMP FPGA Manager. Before starting this recording, I called allocate capacity on the ADRV9371 EBZ Persona. This Persona communicates with the Analog Devices evaluation board of the same name using the industrial I/O driver. And as you can see here in the hardware load status, it is marked active. Viewing its properties, we can see the tuner status for 3 of the channels we've enabled. Here's the RX1 receive channel. It's currently tuned to 950 MHz with a 100 MHz bandwidth, since it's already in use by Ezra. Now, what is Ezra? Ezra stands for Extensible Spectrum Reasoning Application. What it provides is a way to task an arbitrary number of front-end devices to meet certain spectral needs of an individual analysis task, such as a stare or a scan. For each tuner, a waveform is attached for coarse energy detection, that then feeds into the analysis task's inference engine, which handles decisions about collating these coarse detections into signal identification profiles. Additional features include a database for those signal profiles as well as the original RF captures. Also, as part of this process, we produce multiple bulk I/O streams, which you can see here in the REDHAWK IDE as the output of the analysis waveform. The brown-colored line is the noise floor, the blue line is signal, and the green line is the coarse detection overlay. For the sake of the attached REST server, we've further decimated down to a megasample. As mentioned a moment ago, another output from the analysis task are the signal profiles, which you can see pouring into the signal channel. I happen to click a new signal, marked up, which is identifying a megahertz-wide potential signal of interest at nearly 951 megahertz. But operationally, you're probably not going to be using the IDE. Here's Ezra's UI using Geon's Angular REDHAWK framework and REST Python server. The analysis task controls are off to the left, currently set to stare at 950 megahertz with 80 megahertz of bandwidth. Earlier I said the receiver is collecting at 100 MHz bandwidth. That's what the device could tune to, which exceeded the parameters requested by Ezra, including an anticipated margin of roll-off at the upper and lower extents of the receiver bandwidth. Here's the sampling panel. The negative number for resolution disables one of Ezra's features which attempts to normalize the per-bin frequency resolution across a variety of tuners. And here's a mountain of information about the tuner in use by this task. But let's close that panel because you've probably just been watching the plot, right? As you can faintly see, the noise floor is marked in blue, similar to the falling raster, and the signal is in green. The white line is our coarse energy detection status. The configured minimum threshold for triggering a detection in this demo is 3 decibels above the floor estimate. And you can also see the algorithm actively grouping and separating neighboring energy bursts together for further analysis. I hope you liked this conclusion of our Programmable and Persona Device project series, as well as enjoyed this first ever demo of Ezra, running entirely on a ZCU102 evaluation board. The REST Python server, Angular REDHAWK, and SIGPLOT, as well as meta-redhawk-sdr that were used to build this demo are also available on our GitHub. As always, thanks for watching. please feel free to reach out to us for training and support.